Welcome back, everyone. This is going to be part 2 of our trig identities notes here, kind of as an introduction. So we've got some proofs to work through here, so let's hop right into it. So for number 2, we've got sine x minus sine x cosine squared x equals sine cubed x. So again, from last time, you can pick either side, but here it definitely looks like the left-hand side is going to be the more complicated expression where we've got more options to manipulate with algebra. So for this one, there's actually 2 different approaches you could take. So let's go ahead and start our proof just by rewriting the expression we're going to start with. So we're going to start with that left-hand side, and we're going to start manipulating it. Now, there's actually multiple ways we could go about it. So we could notice there's a sine x in this expression. So one pathway would be maybe to factor out the sine x, which would give us 1 minus cosine squared x. But there's also, if we notice, a cosine squared. So alternatively, kind of as a different pathway, we could write this as sine x minus sine x times, well, cosine squared from the Pythagorean identity that we started the notes with is 1 minus sine squared x. So I'm actually going to write 2 different proofs here. So if I go the sine x factoring route, we'll note that we have 1 minus cosine squared. But 1 minus cosine squared is simply sine squared. Again, from that Pythagorean identity. So now I've got sine x times sine squared, which is going to be sine cubed. Proof is done. Similarly, if I take the route where I rewrite cosine squared as 1 minus sine squared, I can distribute the sine x into the expression, so I'll have minus sine x, and then we'll note that the 2 minuses are going to cancel out and become plus sine cubed x. Our 2 sine x's are going to cancel, and then we're going to end up with sine cubed x. And we're done. So note 2 different proof kind of styles here, but they, again, lead you to the same answer. And very short proofs in this case, so not super long sorts of proofs. So don't feel like there's only going to be one approach that works for these. All right, so for number 3, if you haven't already, pause the video, see if you can write the proof. Okay, so we're going to want to choose the left-hand side here again. This will be a common theme. We typically choose the left-hand side. But again, not always. So we'll have some examples where we start with the right-hand side. So we've got sine to the 4th minus cosine to the 4th over sine squared minus cosine squared. So obviously, kind of not sure what to do. We don't have the Pythagorean identity because we have these minuses, not pluses. So we can't set the bottom equal to 1 or something. But we can factor. So we'll note the top is going to be a difference of squares, where it is sine squared minus cosine squared times sine squared plus cosine squared. So again, the top is like an expression like x to the 4th minus y to the 4th, which we could factor, as we just did. Oops. As the difference of squares. And then on the bottom, we'll notice, we've got some like terms that are factors, right? So we're multiplying this, so we can just cancel those out. And what does that leave us with? Well, it leaves us with sine squared plus cosine squared, but we know that that just equals 1. So again, this is kind of almost a single-step proof, so very short. All right, so moving on to number 4. So here's a case where the right-hand side definitely looks like it's going to be where we want to start. So why don't we start with that side? So we've got cosine squared tangent squared theta minus 1. And so we'll definitely rewrite the tangent squared, it looks like. So we've got cosine squared theta. and then sine squared theta over cosine squared theta. And our cosines are going to cancel. So note that's cosine squared over 1. So we'll get sine squared theta minus 1, which is the same as negative 1 times quantity 1 minus sine squared, which is negative cosine squared. But tangent squared is definitely not the same as cosine squared, let alone negative cosine squared. So it seems like this one sounds like it's false. So let's go ahead and check. So let's let theta equal pi over 4, or 45 degrees. So that's an easy value to calculate. So we know that tangent of 45 squared, well, tangent of 45 is just 1, so this is equal to 1. But negative cosine of 45 squared is going to be, well, negative radical 2 over 2 squared. But radical 2 over 2 squared is 2 over 4, or 1/2, so we get negative 1/2. So we can see clearly these are not equal. So this identity is false. So these are not equal to each other. All right, so number 5, we've got cotangent x plus 1 is equal to cosecant cosine x plus sine x. So this one you can kind of do either way, it looks like, maybe. We've got, some expressions that we could rewrite here, expressions we could rewrite here. But I think we're going to want to choose, well, looks like the right-hand side again. And really it's because of that cosecant, it looks like. So let's go ahead and do that. So we've got cosecant x and then cosine x plus sine x. Note the cosine x plus sine x are both linear terms, right? Degree 1. So this is not equal to 1. So note, the Pythagorean identity is only when we square cosine and square sine when we add them together. So be careful not to confuse that as just being equal to 1. So we'll rewrite the cosecant, it looks like. Maybe we'll rewrite these both over 1 since we're going to have to distribute. So we're going to get cosine x over sine x plus, well, sine x over sine x is 1, but cosine x over sine x is equal to cotan x. And we're done. So, again, kind of a more straightforward proof, but one where you want to definitely be careful with which side you choose, because if we chose the left-hand side, it might not be as obvious, but we'd probably want to do some common denominator work. All right, so moving on to number 6. All right, so now we're going to be using t, so just note x, theta, and t are going to be the common 3 variables used most often. Sometimes you'll see alphas and betas as well, some Greek symbols. But don't be afraid, they're just variables. So we kind of have, again, some more choices to make here. So I think I'm going to choose the left-hand side in this case and see where we can get from there. So we've got tangent t minus cotangent t all over sine t cosine t. And looking at the right-hand side, I can see that there's 2 expressions that I want. So I think I'm actually going to split this into 2 expressions to start. So I'm going to write this as tan t over sine t times cosine t minus cotan t over that same product. Okay. And now we're just going to have to manipulate with sines over cosines and cosines over sines, it looks like. So tangent is sine t over cosine t divided by sine t cosine t. And then we'll have cosine t over sine t divided by sine t cosine t. And maybe we'll think of these as over 1, obviously. So in each case, when I'm doing the division here, I could think of this as multiplication by the reciprocal. So this is going to equal sine t over cosine t times the reciprocal of sine t cosine t over 1, which is 1 over sine t cosine t. And then I'll do the same thing with my cotangent expression. And we can see that clearly, this could get a little messy. So definitely be careful with your steps. But this idea of simplifying complex fractions is a very common proof method. So I would make a note of that, especially with things with tangents and cotangents in them. So we'll note the sine t's are going to cancel from the first terms, and the cosine t's are going to cancel from the second terms. So I'll move our statement up here. So the first expression is going to be 1 over cosine squared. And the second expression is going to be minus 1 over sine squared. And that is going to give us secant squared minus cosecant squared, which is exactly what we were trying to prove. And what you'll notice here is if you go in reverse, that would be the proof using the right-hand side, essentially. So it's a little bit tricky, though, because you'd have to get to that step somehow in reverse. So in most cases, there's going to clearly be a more beneficial approach, which in this case would be using the left-hand side. All right, so let's go ahead and look at 7. 7's an interesting one because it's got kind of a symmetry to it. So again, in this case, we can choose either side. So this one, we're going to do it both ways. We're going to do a left-hand side case and a right-hand side case. And we'll kind of do them side by side here. So all right. So they're both kind of equally complicated, and they, again, sort of look similar to each other. So in both cases, we're going to want to conveniently multiply and divide to mix things up a little bit. So if I'm looking from left to right, what I'm missing is this 1 plus sine x. So I'm going to multiply this by 1 plus sine x over 1 plus sine x. Because that at least will get me 1 plus sine x, and then I can mess around with this expression maybe to get a cosine. For the right-hand side, if I'm looking the opposite way, so if I'm going in this direction, I want that 1 minus sine x expression, because I already have a cosine. So let's go ahead and multiply this by 1 minus sine x over 1 minus sine x. So for our left-hand side proof, we'll distribute. So we'll have cosine x, we won't distribute. We'll distribute in the denominator, and we get 1 minus sine squared. So again, we don't really want to multiply terms out unless we can seek some clear cancellation that will occur because of that. So in the right-hand side case, I'll do the same thing, but this time I'll multiply in the numerator. So I'll have 1 minus sine squared in the numerator, and then 1 minus sine x times cosine in the denominator. But now we'll notice in both cases, we've got the Pythagorean identity popping up. So this is really cosine x times 1 plus sine x over cosine squared x, or maybe better to write it as cosine x squared, since we're going to be doing some cancellation. Similarly, I'll have cosine squared over cosine times 1 minus sine. Again, it might be good to rewrite this. It's cosine x quantity squared. So we can cancel a cosine from the numerator and denominator. Do the same thing on the right-hand side proof. And what we'll end up with is 1 plus sine x over cosine x with our left-hand side proof, and we're done. And on the right, we'll have cosine x over 1 minus sine x, and we're done. So again, this would be an example where it's kind of the same sort of level of work depending on which side you choose. So again, it doesn't really matter which side you choose for this example. All right, so we've got 6 more here. We're not going to do all of them together, but we're going to do a couple of them together. So the one that I want to start with is going to be number 10. So for number 8 here, you're going to want to find a common denominator, it looks like. So find a common denominator and look for some special identities. For number 9, well, I think we're just going to need to simplify that since those things are already equal to each other. So we really just want to show that that bottom is equal to 1. For number 10, though, we've got something like what we just worked on, number 7, but now combined together. So it looks pretty obvious we're going to choose the left-hand side here. So we're going to start with that left-hand side. So we got 1 plus sine theta over cosine theta plus cosine theta over 1 plus sine theta. So we have reciprocals of each other, essentially, which is kind of interesting. And we want to show that that's equal to 2 secant theta. So, like we've done before, we're going to want to find a convenient common denominator, it looks like. So I'm going to multiply 1 plus sine theta over 1 plus sine theta to the left-hand term, or the first term, I should say. And then we'll multiply cosine over cosine to the second term. So we're going to get 1 plus sine theta squared plus cosine theta squared all over cosine theta times 1 plus sine theta. Okay. And now, well, it's not quite obvious, right? So we're hoping, since that's secant, that we just end up with a cosine. So looking at our 2 terms here, it looks like we're going to have to expand this binomial. So multiplying this out using the distributive property, we'll get 1 plus 2 sine theta plus sine squared theta. And then again, we still have plus cosine squared theta adding on there. So we've expanded that binomial quadratic. All right. So looking at this, it's a little bit unclear. So take a moment, see if you notice it. If we look there, we've got sine squared plus cosine squared, but that is just equal to 1. Well, that means that the top is really just 2 plus 2 sine theta over cosine theta times 1 plus sine theta. And then I can factor out that 2. And that means our 1 plus sine theta is going to divide out. And we'll be left with 2 over cosine theta, which is 2 secant theta. And we're done. So a more complicated sort of version of problem number 7, because we're doing common denominator work on the same side, but still just kind of working through step by step to kind of manipulate and simplify. All right, so for number 11, we'll notice that the statement is going to be a little bit messy as well, it looks like. So I'd say start with the left-hand side. But I'll tell you ahead of time, this is going to end up being false. See if you can figure out why it is false. And then we're going to take a look at number 12. For number 13, again, we'll want to look for some special expressions in here and then simplify. But number 12, that'll be the last one that we do here together. So let's take a look at this one. Again, kind of in between on what we could do. And we'll notice that this expression we've seen before. So we could have also written this identity as 1 plus sine y over cosine y as well. Right? So from problem number 7. So here we've got another variation, which is going to be this secant and tangent so let me take a look at the left-hand side version of this. So if we do the left-hand side, we'll get secant y plus tangent y, which obviously we're going to have to rewrite with sines and cosines. So we've got 1 over cosine y plus sine over cosine. But what is that? That's just 1 plus sine y over cosine y. So from here, we're just going to repeat what we did for number 7. All right, so it's the same exact proof, just with a couple of additional steps. But you might wonder, well, what if we started with the right-hand side? So you might try that. Maybe just challenge yourself a little bit in reverse. All right, so that's going to conclude the notes on identities. Again, the ones that we've skipped, you can check the completed notes online for a short proof of, but those would be ones that are going to be sort of similar to what we did previously on this first page with all of these different proofs. So if you have any questions, definitely let me know, shoot me an email, drop by class if you can. Otherwise, until I see you again.